Hi. Hello, everyone. My name is Carlos Matallana, and I work at Polygon zkEVM, and I'm the protocol team lead. Basically, today I will be just talking a little bit about the next major protocol upgrade that we'll have. It will be the Fork.6. You will see later on all the changes that we have done in the zkEVM. So first of all, I want to do a little introduction about what is a fork in the zkEVM, because it's a little bit different rather than in Ethereum. Why forking the zkEVM? There are different aspects to take into account when doing that. A little bit the history that the zkEVM in mainnet, all the forks that we haven't done previously. Then I will just talk a little bit about the futures regarding the Fork.5 that we did on September. What are the new features that will be introduced in the Fork.6? And I would say what we have in mind that could be the future ones. Okay, so first of all, introduction. What is a fork in the zkEVM? Well, as you may know, in Ethereum, there are this kind of hard forks, and they have different names like Berlin, London, Shanghai, the Cancun one. And basically, those upgrades to Ethereum protocol are proposed by the EVM developers. They just introduce some new opcodes, some new EIPs, consensus rules, and basically what it happens, it's a hard fork, so the chain is forked, and basically the majority decides which is the canonical chain. So they decide to go to the, I would say, to the left or to the right. So they choose the canonical chain in order to follow. This is regarding Ethereum, but what happened in the zkEVM? In the zkEVM, it's basically an upgrade of the smart contracts. So we basically have a definition of what we call the state transition. So you have some transactions, and the state root, and when you process the transaction, then you have an output state root. And this is the state transition. And what the smart contract assures you that this state transition is valid? Well, it's the verifier. If you upgrade the verifier, it means that you are upgrading, the zkEVM. It means that you are kind of forking, because the state transition function will be different, in fact. The thing is like, okay, I'm just upgrading, I'm just doing a fork, but as in Ethereum, you can choose whether to stay in a previous hard fork or whether to continue in the new one. So in the zkEVM, basically, we have this time lock smart contract. It's very commonly used in the protocols, I would say. And here, this time lock smart contract just assures you propose the upgrade, and then before executing the upgrade, you have some time. So you give to the user some time in order to leave the contract if necessary. Okay, and here is why forking the zkEVM. Okay, as I mentioned previously, in Ethereum, they are proposing new opcodes for more efficiency, more gas efficiency, new precompiled smart contracts maybe, because of the zkSNAR, for example, so whatever. And in order to adapt to these new EVM opcodes, the zkEVM also needs to do a fork, okay? Also, there are some specific features that are very related to the zkEVM. I will comment it later, the effective gas price and the data compression, but they have no relation to the EVM itself. It's more a specific feature of the zkEVM. If we want to update it, we will do just another fork. Also, well, as you may know, in zero knowledge ecosystem, there is a lot of research ongoing, a lot. So we are kind of always willing to embrace all this new research that has been done. And basically, it's about new hash functions, new verifiers, new optimizations, and so on. When you want to integrate those into the zkEVM, you also need to do this kind of fork. Also move to a type 1 zkEVM. What does it mean? It means that, well, currently there are a lot of zkEVMs in production, in mainnet, but I would say that none of them is a type 1 zkEVM. Type 1 zkEVM means that the zkEVM behaves exactly as the EVM. There are type 2s, there are type 3, there are type 4. There is a blog post of Vitalik explaining them. And if you want to move forward, if you want to move from the type 2 to the type 3, type 2 to the type 1, so you need to do protocol upgrades as well. So it's meaning that you need to do a fork. And removing training wheels, well, as you may know, zero knowledge, very cutting-edge technology. I mean, some parts of the protocols are a little bit centralized in order, I would say, for safe. And in order to remove those training wheels in the smart contracts, also you need to do some forking. Okay, so this is basically the fork history that we had. You can notice that I started in fork 4. The previously 3 forks, they were in testnet. Then last month, we introduced the fork 5, and probably in Q4 2023, we will introduce the Fork.6. And now I'm going to explain the 2 features of the fork 5 and the 3 ones on the Fork.6. Regarding the fork 5, okay, you may hear about in Shanghai hard fork in Ethereum, it was an addition of an opcode. It was the push 0, okay? This opcode, I would say it's kind of straightforward opcode, no? Instead of using push 1 and then 0, 0, you just call the opcode push 0 and you insert 0 into the stack and that's it. Then you basically save 1 byte and basically save 1 gas. This is very important. Well, basically, it's safe bytecode to be stored on the state tree in Ethereum, okay? And basically reduce costs when you deploy some smart contracts. Why? This is very important. Well, as you can see here, there is just an implementation of the push 0, 1, 2, 3, 4 lines, not that much. This is mainly the zero knowledge assembly language that we are using. But here the important thing is that you can see that there is no so much lines here in the push 0. And why the addition of the push 0 implementation is important? Well, the push 0 implementation was added to the Solidity version 0.8.20. So what happens is you write a smart contract with this Solidity version, and you compile it, and then you deploy it on the EVM. Okay, it's perfect. Nothing happens. But what happens if you do exactly the same, okay, but you try to deploy it in a layer 2 network? That the push 0 is not supported, so it will just trigger an error. So, and one of our developers, Jesus, just make a comment in the Solidity repo just saying, hey, be careful of that. Well, nobody cares. But, well, turns out that Hard Hat, one of the most development kits used in the ecosystem, basically just do kind of a rollback. Okay, so by default, it was set that by default uses the Shanghai hard fork, which includes the push 0. Okay, but Hard Hat just make a rollback that says, okay, don't use the push 0. Okay, by default. I mean, if you say to use it, then use it. But by default, not use it. Okay, I would say this cause some issues and troubles to developers. Okay, and this is very important because the layer 2 networks, we are aiming to be exactly the same as the EVM. So we should follow, obviously, the EVM, because normally they introduce these new IPs in order to be more gas efficient or bytecode efficient or whatever. Okay. I think that currently we are the only ones that support push 0 in mainnet. Next one, it's effective gas price. What is this? Well, basically, this is just a single byte, okay, that allows us to charge less gas to a user. You may know that in an Ethereum transaction, there is this gas price, which is a signed field. And then this byte basically allows us to charge a percentage of this gas price that the user signed. So basically, you charge the user the gas price that he signed or less. Okay, this is a trick. I would say, well, it's not a trick. This is a protocol definition that we made in order to charge fair gas prices to the users. Because as you may be aware of, in layer 2 transactions, the cost of a layer 2 transaction is basically the data availability cost. And how do you know the cost of data availability? So you need to know the layer 1 gas price when you publish those transactions on chain. Okay, and you don't have this price on layer 1, real time, in layer 2, sorry. So layer 1 gas price needs to be moved to layer 2, but it's kind of difficult to do that. Furthermore, EIP 4844 will be introduced in the Cancun hard fork. How do you price the data that will go into the blobs in the proto-chain EIP? You don't know in layer 2. So thanks to that, we kind of computing off-chain, and we can apply this kind of reduction to the user transaction. Okay. Of course, there is always a trade-off. Here the trade-off is basically that we have kind of a centralized sequencer, so the sequencer can choose this percentage freely. Here, the cool thing of our protocol is that the user, it's freely move out of the protocol if he wants to do so. Okay, what about the Fork.6? So the Fork.6 basically introduced one important concept that we didn't take into account at the beginning of the protocol. Okay, this concept is the block. Okay, you may hear about, you know what is a block in Ethereum? Okay, so that. We have a badge. And we thought at the very beginning that the badge will be the block. Okay, so we name it that differently in order to not to confuse block and badge. And this badge, the header of a badge, we have the timestamp and the global exit route. And all the transactions that fit inside the badge shared this kind of badge header, which includes the timestamp and the global exit route. But we realized that we can add a lot of transactions into a badge. Okay? So what happens if you take just 30 seconds to add a lot of transactions to this badge? Because of course we want to fulfill the badge as its full capacity. It's very important. It happens that the very last transaction has the timestamp span would be 30 seconds. So what we introduce here in order to improve the performance is this concept of block inside the badge. Okay, so now in the Fork.6, what we have is, I would say, a granularity of this timestamp and global exit route inside the badge. Okay, well, I already said this allows multiple blocks to be built inside the badge. Nowadays, blockchain, if you have a block time of 30 seconds, 40 seconds, decentralized finance applications, oracles, and so on, they don't like that. So they need more granularity in timestamp, probably 3 seconds, 4 seconds, 5 seconds, 12 seconds in theory. This also will increase this batch performance. This looks like more a standard blockchain approach, since we didn't have this kind of block concept inside the zero-knowledge circuit, inside the batch, but we will have it in the Fork.6. So basically, it looks like more a blockchain approach. Okay, and as I mentioned, it's very important for oracles and centralized finance. And when we include this change kind of block inside the batch, then what we could do is a block hash, but in layer 2. You may know that, of course, there is a block hash in layer 1. So if you call to the RPC endpoint and you receive some data, thanks to the block hash, maybe you can verify that that data is correct or not. Okay. We do not have this in layer 2, so you need to kind of trust of the ERP-set node. But with this, we're going to introduce this block hash layer 2 in the batch in layer 2. Okay? So it means that when you call the RPC and you get some information, you can kind of verify that this information is correct. Otherwise, you need to trust the RPC. Well, this is basically the specification. It's a little bit different rather than the Ethereum. We basically took all the data. So we built a sparse Merkle tree using the hash function, the Poseidon. And we don't have multiple trees like in Ethereum, that you have the transaction tree, the receipt tree, and then you build the block hash. No, here we only will just have one Merkle tree, which we call block info tree. And inside this block info tree, it will be, well, of course, the previous block hash, and the end is the blockchain. Block number, gas limit, timestamp, global exit route that got used. Here, the different field is the global exit route, which is used by the bridge. And, well, the transaction data is probably exactly a little bit the same when you compare to the Ethereum. So you hash all the signed parameters of an Ethereum transaction, and later on the outcome of the transaction, which will be the status, the accumulated gas user, and all the logs triggered by the transaction will be hashed as well and added into the tree. And at the very end, this will be the block hash layer 2, is what we call. And the precompiled one. Well, the precompiled is just a table, just to let you know what we are currently working on. And basically in the Fork.5, we just supported is recover an identity. And in the Fork.6, what we are currently working very hard in order to support the SHA-256, identity mod exp, and elastic curve ones related, add mul and pairing. Okay. This is very important in order to be from type 2.5 to type 2 zkEVM. Okay, we decided to not put a lot of effort in the RIPE-MD 160 and the Blake 2F precompiled because they are not used too much in Ethereum, and it will take a lot of time to implement in the zero knowledge part of the zkEVM. So what about the future? Well, you may know that the future basically is EIP 4844. What we will do is we will add a new circuit that we will call zkBlob, and this circuit will manage the Ethereum blob, okay? This is very important. This is very important because it will reduce gas cost from data availability from 16 gas to 3 gas per byte, okay? And basically this will repercute the layer 2 transaction cost of users. If the data availability cost reduces, the layer 2 transaction cost will reduce exactly the same. And also, we are working very hard on the data compression. Data compression, what we are going to do is a custom data compression protocol. Okay, so we study the Ethereum transaction fields, basically, and okay, how to compress them. If you compress them, then you put less data on chain, then the transaction will cost less on chain, on layer 2, on the user side. Okay? And these are the 2 fields that we're working on, probably Forks 7, 8, and 9. We will see. And that's pretty much. Thank you.